All right. So today we will bite the bullet and we will convert all your favorite angular quantities into vectors. And there was much rejoicing. No, this is not an April Fool joke. And to do this, we will use something that you have assured me you all know, and we will review the cross product between two vectors. But let me start by recapping what we saw last time. So we were worrying about things that roll without slipping. And if it's a perfectly round object, and there's no slipping, that means that the distance around the circumference of the round object must be equal to the distance traveled or the point of contact on the flat surface, and that leads to this kind of an expression. And of course, we can differentiate with respect to time as many times as we like, and that's still a good expression. And we saw maybe in a couple of problems in recitation that things get a little bit tricky if the surface that you're rolling on isn't flat. If it's curved, then there's a slight correction. Depending on the curvature, it may be a big correction, but I'll have that filed away. We found that the kinetic energy, because of this marvelous theorem that said that the kinetic energy of a collection of particles is equal to the kinetic energy in the center of mass frame of all the particles, plus the kinetic energy of a single particle that has all the mass and moves at the center of mass velocity. Okay? And then we saw that, we had an expression for rotational kinetic energy about the center of mass. And so therefore, if we're worrying about a rigid object, then the kinetic energy may be expressed this way always. Sometimes it's more convenient if it's just doing a straight rotation about a point that isn't necessarily the center of mass to use the moment of inertia about the point or the axis around which it actually rotates. And then you don't have any worry about the fact that, this just went, okay. Any worry about this term, it would be a pure rotation, and you would just have 1/2 I omega squared. We saw also the rotational work energy theorem, which allowed us to define the rotational work done when a torque rotates through an angle. And we use that to help understand what's happening when an object rolls without slipping down a plane. Is there any energy loss to friction if it rolls without slipping? It just transferred, right? Okay.